Hello everyone. Today we're going to talk about best first search with branch and bound pruning for solving the traveling salesperson problem, or TSP. We talk about solving the knapsack 01 knapsack problem, okay, and we use the some bound, okay, to see that what's going to be the best or the maximum gain, maximum bound for a node. So we are going to expand the node that has the higher bound at first. So that's using the best first search and using the the bounding when we're using the branch and bound approach. So as I said, on the knapsack problem, the goal was to find start with the bound that has is maximum, or like the one that has the high value. In the TSP problem, what we're going to do is we're going to again do the same approach, but this time we are going to use the minimum bound, okay? Because the goal in this problem is finding the shortest path, okay, that connects every city to each other, okay, on the TSP problem. So here we have one example of the TSP problem, like the distance between cities. So let's say we have 5 cities or 5 nodes, and these are the adjacent C matrix of these nodes. So let's say from node 1 to node 5, and these are the distances. So how we can calculate the bounds? So the bound is, as we said, is the minimum distance between the cities. Okay, so if we want to find the minimum bound, okay, for starting node, okay, we can see that what's going to be the minimum distance in every row that we have. Okay, because and we can also start from any node. Okay, let's say that we are starting from one node, node 1 or 2 or any other node. Okay, because TSP doesn't matter which is going to be your start, but given any start node, you can go back to the same source. So here, let's say that we are starting from node 1. Okay, when you're starting from node 1, what's going to be the minimum distance, okay, from node 1 to any other node? Okay, so that's the distance to node 3. That's is equal to number 4. So we have number 4. Then I'm gonna see that what's gonna the minimum distance, okay, now from the second one for B, that is for any other node, that is equal to 7, either node 3 or node 5. So this is equal to plus 7. What is the minimum distance from node 3 to any other node? Okay, so that's gonna be 4. And what's the distance from node 4? The minimum distance is equal to 2. And what's the minimum distance from node 5 to any other node? That is equal to 4. And if you sum up these numbers together, okay, this is equal to 21. But keep it in mind that it doesn't mean that we found the shortest path and we solved the TSP. Okay, this is the bound. So it means that, okay, we cannot find another path that is less than this 21. Okay, because we found, okay, we just sum up all the values, all the path from any node to any other node that was minimum. Okay, so from node 1 to any other node, from node 2 to any other node, and so on. So that is our bound, and definitely any path that we found, okay, will be at least will be 21. Okay, might be 21, okay, but is definitely is not less than 21. Okay, now let's solve the the TSP problem, okay, and using this best first search with the branch and bound pruning on the example that we provided here. Okay, so as we said, the first node, okay, will be the node 1. Okay, you can, again, as I said, you can choose any node, but let's just start with node 1. And starting from node 1, the minimum the bound is equal to 21. So instead of using the maximum bound, this time for TSP problem we are using the minimum bound. Okay, so the node 1 is selected, and as we calculated the minimum bound, okay, using the node 1 as a start node, it was 21. So we sum up all the values, that was the minimum on every row. That was saying that from any node to other nodes in the graph. So here we have four options. From node 1, either we can we can go to node 2 or node 3 or 4 or 5. Okay, so that's our options from node 1. So now let's calculate the bound for this node that is node 1, 2. It means that we already we moved from node 1 and pick node 2. So let's see what's going to be the bound for this one. So here at first we went from node 1, okay, to node 2. So if you look at the adjacency matrix, it says that the cost of going from 1 to 2 is equal to 14. So we have 14 cost so far. Okay, so the cost so far is 14. And now this should be summed up with the cost of going from 2 to other nodes. It means that from 2 to 3 to 4 to 5, and again coming back to 1. So similar to what we did for node 1, okay, when we found the minimum bound, we're doing the same thing. So from node 2, okay, so what's going to be the minimum is, okay, not node 1 again itself. Okay, we have the minimum should be between 7, 8, and 7. Okay, so between these three numbers that we have here, we're going to find the minimum one that is equal to 7. Okay, we are not going back here from like the 2 to 1 itself, okay, because we already been. So here's 7. Then for the node 3, that is the third row, okay, it's going to be minimum cost. But here we are already at node 2. Okay, we cannot go from node 2 like from node 3 going back again to node 2. Okay, so then we are like eliminating the cost of node 3 to node 2, and then the minimum cost now will be 4, 7, and 16. Okay, we are not considering zeros, okay, because zeros are the cost to go into this node itself. Okay, we are not going to add the reflexive one. So the minimum is equal to 4. For the node 4 also we have the same thing. Okay, we are already at node 2, so we are not going to go from node 2 to 4 and going back to to 2 again. So the minimum will be between 11, 9, and 2. That is going to be equal to 2. The next node, okay, is node 5. So the minimum is between 18, 17, and 4. Okay, again, not from 2, okay, because we are not going back from 2 to itself. So it's going to be node the value 4. So if we sum all these values together, these sum up to equal to number 31. So I am writing the bound 31 for this one here. Okay, so I am gonna do the same thing, okay, for node 3. Okay, so we're gonna do the same thing for node 3. And if we just do the same thing, okay, to write the values here, so I'm not gonna calculate the everyone, but we are going doing the similar approach. So it's gonna be 22, okay, here. This is gonna be 30, and from 1 to 5 gonna be 42. Okay, and so the best first search, okay, on the the branch and bound approach says that use the one that is best. Okay, so we are expanding the node that has the best result so far, or the best bound so far. And here best bound means the one that has the minimum bound. Okay, so between these four nodes that I have here, I have the node 1, 3 that has the bound of 22 that is minimum. So I'm going to expand that node. Okay, so next we'll go and expand node 1, 3 and see that how it goes. Okay, we said that we are going to expand the node 1, 3 because now it's the most promising one and is the best one that we have so far. So if we we have the expand the node 1, 3, we have three options: going from node 3 to node 2, or to node 4, or to node 5. And we're gonna see that for each one what's gonna be the bound. So from node 1 to 3, the cost is, if you look, is equal to 4 based on the adjacency matrix. Okay, so from 1 to 3. Then from going 3 to 1, that is here. So we are going this path. Okay, from 3 to 1, 3 to 2 is equal to 5. So the cost is 5. And now okay, we are at node 2, we are gonna see that if we go the other options, what's gonna be. So we cannot go back to node 3, okay, because we already visited node 3. So we are checking now the minimum cost for node 2 between 14, okay, and not including this 7 here, okay, because we said already visited node 3. Between 14, 8, and 7, the minimum is 7, so we have 7. Then the node 4, okay, so what's going to be the minimum of this one? It still is number 2, that is going from 4 to 5, so it's equal to 2. And for the fifth one, for the last node, this also the minimum is equal to 4. So if we sum these all numbers together, again, they are summed to 22 here. I'm gonna do the also the 1, 4, 1, 3, and 4, but like I'm gonna just write the value, the bound that calculated for 1, 3, and 5. So from going 1 to 3, the cost was 4. From 3 to 4, if you look at the cost is equal to 7, so 4 plus 7. And now we are gonna go from node 4 to any other node. Okay, so from the minimum cost for every other node. For 2, the minimum cost is still 7. For number 4, the minimum cost is going to 2, that is equal to 2. Okay, and for the last one, it should be equal to 7. So together sum up to 27. And why this is the case that is equal to 7 here? So from node 5, we cannot go back to node 4 or 3. Okay, so these are eliminated from our choices. So 4 and 7 are eliminated, and the only option that we have is going back to node 1 or going back to node 7. Okay, so that's going to be the minimum, going to be 7. So together these values will sum up to 27. Now I'm going to just show the value, or we can do it also for node 1, 3, and 5. Okay, just to see some more examples. So from node 1 to node 3, the cost is equal to 4. From node 3 to node 5, the cost is equal to 16. Okay, so this cost is equal to 16. Now we're going to node 2. So from node 2, we cannot go to node 3 and 5. Okay, so we are eliminating this one and this one. So the minimum will be between 8 and 14. That's gonna be 8. Now we have node 4. Okay, node 4, we cannot go to node 3 or 5, okay, because we already visited these nodes, and the minimum will be between 7 and 11, that is equal to 7. And for node 5, okay, we cannot go back to node 3, and the minimum is going to be equal to 4, that is going to node 4. So if we sum all these values, this sum up to number 39. Now let's see that what we have done so far. So first we expanded the node 1, okay, and the bound, the minimum bound was equal to 21. So it means that we cannot find a path that is less than 21. So that's the minimum value that we can reach. Then we expanded the next best one, okay, that was node 1, 3. Okay, we first we calculated node 1, 2, node 1, 3, node 1, node 4. And node 1, 5. In between them, among them, like the 1, 3 was the best. So let's write that was the first one, then was the second one, then that we expanded. Okay, and now if you look at the numbers that we have here, so we have 31, okay, that unexpanded yet. So here this one, this one, this one, and this one, this one. So between these, okay, the node that has number 22, okay, that is node 1, 3, and 2, has the minimum cost. So we are going to expand this node and see if we can reach better values or not. So I'm going to just expand this node here. So let's say that this is node 1, 3, 2 here. So 1, 2, 3 here with the 22 here. And now I'm going to expand it here. So one node will be 1, 3, 2, 4, okay, and the other node will be 1, 3, 2, and 5. Okay, and I cannot expand this node anymore. Okay, the reason is obvious. So I have visited node 1, 3, 2, 4, and I have no other option to except node 5. Okay, so this is equal to within one node 3 to 4 and 5, and then going back to node 1. Here also we have no option. After visiting node 1, 3 to 5, I have no other option except going to 4, then going back to node 1. So if we calculate this one here, just sum the value that we have here. So from going from node 1 to 3, the cost is equal to 4. From 3 to 2, the cost is equal to 5. Okay, then going from node 3 to 2, that's gonna be equal to from node going from 2 equal to 4 is gonna be 8. From 4 to 5, the cost will be equal to 2, and from node 5 going back to node 1, that is equal to 18. So if we sum up these numbers together, okay, so it's gonna be 30 to 38, and together it's gonna be 37. Okay, so that's gonna be one path. Okay, so the cost will be 37. And similar to that, if we calculate the value or the length here, this is not the bound anymore. This is the actual length. Okay, because we already visited all numbers and we went back to node 1. So the length is equal to 37. So similar to that, if we're going to calculate the length, okay, for this one, 1, 3, 2, 5, then going back to 4 and 1, the length is going to be 31. Okay, so definitely this node is not like what we are looking for. Okay, so we are going to ignore this solution, okay, because we found a solution that is 31. So definitely we can like eliminate some other nodes, okay, because this one here, when we had the node 1 and 5, so this is 42, so we don't want to like to go and expand it anymore, so we are ignoring this one. And also that one has that also has 39, okay, because we found like the length that is equal to 31. Okay, so these 42 and 39 was saying that we cannot find a number that is less than 42 and less than 39. And because we found a smaller length, okay, we are not expanding those nodes anymore. So they are pruned from our state space tree. Now between the nodes that we have 31, 27 here, so we also we can like ignore this one as well. Okay, the reason is that we found the 31, so there's no reason like to expand this node as well, because it's not less than 31. So the only two node that I have now that's not expanded yet is this node, okay, 134 with the cost with the bound of 27, and this node that is 14 with the bound of 30. Okay, so it means that again these are the minimum values, so it doesn't mean that it's gonna be less than that. So next I'm gonna just show you that what's gonna be the solution for this problem using the best first approach and branch and bound pruning. Okay, so the next node we said we were going to expand is the node 1, 3, and 4. Okay, so here we have two option. Okay, so either going from 1 to 3, 4 to 5, then no other option remain except like going to 2, then going back to 1. The other one is going from 1 to 3 to 4, then going to 2. Then we don't have another option except going to 5 and definitely going back to node 1. So if we sum all these values together, okay, this is really obvious. The path are exactly determined at which path should we go. Okay, if we sum up all the values here from, for example, from 1 to 3 is equal to 4. Okay, so 4 from 3 to 4 it is equal to 7. From 4 to 5 it is equal to 2. From 5 to 2 is equal to 7, and from 2 to 1 this is equal to 14. So if we sum all these values together, then we are gonna reach the value 43. And similar to this one, if we calculate the value for the other node will be equal to 34. Okay, and as you see, both these values are like greater than the shortest path that we found so far, that is equal to 31. So it means that they are not our solution. So this is gonna be eliminated from our solution space. And so it means that because this node, okay, didn't give us a better solution, so this node also goes away. And here was this nodes that I expanded. So if I'm gonna just this star and here, that was there. So now the only node that is remain is the node 1 and 4. Okay, the 1 and node and 4, that we can expand this one and see that what's gonna be our like best solution. Okay, the next node that was promising and has the best first search was 30. Okay, so we are gonna expand this one, that is 1, 4. So we can expand like these nodes has 1, 4, 2 option, 1, 4, 3 option, and 1, 4, 5 option. Okay, so if we calculate these values for bound for these 3 nodes that we have here, okay, it's gonna be 35, okay, and 38 and 30. And because 45 and 38, okay, are greater than this value that we found, okay, the solution, that 31, so we are not expanding them anymore, so they're going to be eliminated from our solution space. Okay, so there is no reason to continue these 2 nodes that we have here. So now the only node that we have here is the node 1, 4, and 5. Okay, so there is if we also expand these 2 nodes here that we have, okay, so it's gonna be either so let's have it here. So I'm gonna one, 4, and 5 with the cost of 30. So we can either go to 1, 4, 5, 3, okay, then we don't have any options except going to 2 and going to 1, or we can go this path, going from 1, 4, 5, going to 2, and there's no other option except going to 3 and going back to node 1 here we have. So here if we calculate the numbers that we have here, so 1, 4, 5 to 31 gonna give us the cost of 30, okay, and the other one will give us the cost of 48. Okay, so we are expanding this one, and we find there's no more expanding, so that's it has the length of 48. That's not the solution, and we found a length, okay, that is less than 31, so that's going to be our solution. So 1, 4, 5, 2, 3 and 1 is going to be our solution.